Alright, today we begin Unit 2, Part 2. We're still working with polynomials, but we are taking polynomials to the next level. Up until now, we've been working almost exclusively with x squared, quadratic, but now we're going on and we're going to deal with cubic, quartic, quintic, and what have you. Okay, let's start off with a quick review of end behavior. And let's see if we can extend this to the new types of polynomials. Now, when we talk about end behavior, we are talking about what happens on the left and what happens on the right. So looking at your typical quadratic equation, all right, and here's the most basic one possible, all right? Sometimes we call this a parent function because all of the other quadratic equations are sort of modeled after this one. On the left it rises, and on the right it rises. So in words, I'm talking about end behavior. And looking at a quadratic equation that has a negative leading coefficient, all right, it becomes an upside down parabola. So now on the left it falls, and on the right it falls. So we've memorized that a quadratic, x squared, that's going to be a parabola. Now I want you to memorize something else. Here is your basic cubic equation. The most basic form of a cubic function is y equals x to the third power. Now I just want you to memorize that in general, a cubic function, as far as end behavior, it's going to behave like a capital N. Can you sort of see an N when you look at this shape? I know it's a little bit of a stretch, but see, this sort of works like a capital N. Anyway, a right side up N, if you can kind of see this as an N a little bit, you know, if I were seeing this a little more pointy, okay? An uppercase N has the same end behavior as a positive cubic function. So I just want you to memorize that, all right? A positive cubic function is going to behave like an uppercase N. All right, now what is this end behavior? Well, on the left it falls, and on the right it rises. All right, it's fine and dandy. Now, if I take that function and I put a negative in front of it, okay, how does that change things? Well, just like when we look at a quadratic, a positive is going to be this upward facing parabola, but a negative turns the whole thing upside down. So the same thing will happen here. By putting a negative in front, it's going to turn the entire function upside down. So it's going to go from a right side up N to kind of this upside down N. Okay? So an upside down N shape like this, this will change the end behavior. Now on the left, it rises, and on the right, it falls. Okay? Now, keep that in your mind. So looking at number 3, describe the end behavior of p of x, and here's the function. Now, but this time I didn't give you a graph. So, you know, how are you supposed to know what the end behavior is like without being given a graph? Well, it's because of this. Just look at the degree. All right, this is a cubic function, looking at that x to the third power. And all cubic functions have the same end behavior, except for you have to pay attention to if they're positive or negative. Now this one, you can see that it is positive. So without knowing the exact graph, I know that the end behavior is going to work like this. All right? It's going to have the same end behavior as all positive cubic functions. So it'll have the same end behavior as this one that we did, same as problem number 1. Okay, so we will just say on the left it falls, on the right it rises. And it's a good idea just to make a quick little sketch before you do it. So we will say on the left it falls, on the right it rises. Okay? We knew it would make this N shape because it's cubic. We knew it would be right side up because there's no negative in front. The leading coefficient is positive. Now look at number 4. Describe the end behavior of this guy. Make a little sketch for this function. See if you can do it before I do. Make a little sketch right here. Hopefully you recognize that this is a quadratic trinomial. All right, this is a quadratic function, and because it's quadratic, it's going to make some type of a parabola, right? It's either going to be like this, or it's going to be like this. Now, which one is it going to be? Well, hopefully you know that it's going to be an upside down parabola because it's got that negative in the front. Okay, so it's a negative quadratic, so it's going to be upside down parabola. So then we can go ahead and say the end behavior. On the left it falls, and on the right it falls. Okay, now look, we learned end behavior using arrow notation, and that's coming. All right, we'll go to that, but I wanted to make sure that you have the concept down, and you know, if you do the notation wrong, that's one thing, but right now I'm focusing more on, do you understand the concept? All right, now look at number 5. Describe the end behavior of this function. Now, so far all we've talked about were cubic functions and quadratic functions. All right, third power and second power. And when I did these models at the beginning, again, we talked about x squared, we talked about x to the third power, quadratic, cubic. But now here out of nowhere I have x to the fifth power, quintic. We haven't talked about that, so how can I expect you to do it? Well, it turns out that all odd degree functions have the same end behavior. So it doesn't matter that this is a 5. What matters is that this is odd. All right? Because it is odd degree, it's going to be the same, it's going to have the same end behavior as a cubic. All right? Whether it's 3, 5, 7, 9, if it's odd degree, it's going to have end behavior like a cubic function. And being more specific, this is a negative leading coefficient. So it will have the same end behavior as a negative cubic. All right? All odd negative functions are odd degree negative leading coefficient. They're going to have the same behavior. Now we learned that a cubic function has end behavior like an n. It works like a capital N. And if it's a negative, it's going to be like an upside down n. So in your mind, you should be picturing an upside down n. And you know, obviously, if you make that upside down n a little more curvy, then you've got a function to play around with. So that's the idea. Now, in truth, okay, as you go to make a little sketch for yourself, okay, so it's odd, so you know it's going to have end behavior like some sort of an n. It's negative, so it'll be like an upside down n. All right, so the end behavior will work like this. So we will say on the left it rises, and on the right it falls. All right, so there's your end behavior right here. Now, just to be clear, the graph won't actually look like this, okay? It will just have n behavior like this. But as I go to higher and higher degree, what happens is there will be more turns in the graph, but it'll have the same n behavior. For example, the fifth power graph may look more like this. All right, I know it's going to have that same n behavior, so I'm going to start it off the same way. But instead of just making an n, okay, it'll have an extra turn in it. It'll have an extra hump, okay? But if you look at the n behavior of this function and compare it with the n behavior of a cubic function, okay, a cubic function would do like this. All right, so even though because it's fifth power, it has extra turns in it, if all we are talking about is the n behavior, the n behavior will be the same. But please don't think that the actual graph is going to look like a cubic. It will, the higher this number is, the more turns there will be in it. Say if this was the seventh power. All right, imagine I scribble this out and make it a 7. Okay, to make this into the seventh power, the n behavior's got to stay the same, but yet I need an extra turn in it. Okay, so I guess I got to start it over again. So it would be like this. So far there's cubic. All right, there's fifth power. So put another hump in it. Now this would be what your basic graph of a seventh power function would look like. Okay, but again, the n behavior is still the same. The n behavior is the same as a cubic function. Okay, so when you make your little tiny sketch, you can just sketch a cubic for all the odds, because we're only talking about n behavior. Anyway, I've talked about that too long. Look at number 6. When you make your tiny sketch, is it going to be a parabola or is it going to be an N shape? Well, just like all odd degree functions are going to behave like the N, all even degree functions are going to behave like parabolas when we talk about N behavior. So because this is even, this is going to be, the N behavior will be like a parabola. Because it is positive, the N behavior will be like an upward facing parabola. Okay? So, on the left it rises, and on the right it rises. Okay? Now, one more time, please understand that if I were to actually graph this, it wouldn't be a parabola. It would just have the same N behavior as a parabola. The reality would be more like this. Again, the higher the degree, the more turns it's going to have in it in general. A quartic function in general will sort of look like a W. All right, it will have this general shape to it. So it would actually look more like this. But if all we care about is N behavior, all right, I'm hoping you can see that the N behavior of a parabola would be the same as the N behavior of a W. So we don't really need to worry about the fact that it's actually a W. We can just use the parabola for the N behavior part. Okay, but don't think it's actually a parabola. It's not. Did I confuse you? I hope I did not. All right, now don't forget your actual arrow notation, okay? When we talk about on the left, it rises, on the right, it falls, we would actually write it this way. Instead of saying on the left, we'd say as x approaches negative infinity. And instead of saying it rises, we say f of x approaches positive infinity. You don't actually need the plus sign. Okay, so please remember what I told you. This part of N behavior never changes. All right, everything I just highlighted in yellow, that's the same every time. You see it? It's the same thing right here. All right, it's the same thing here. It's the same thing for all 4 cases. That's because in all cases you say on the left and then on the right, on the left, on the right, on the left, on the right. And as x approaches negative infinity, that just means on the left. As x approaches positive infinity, that just means on the right. So the only thing that's going to change is if it rises, we're going to put positive infinity. If it falls, we're going to put negative infinity. All right, so falls, rises, that's negative infinity, positive infinity. Rises, rises, positive, positive. Falls, falls, negative, negative. But the rest of it stays the same. Okay, all of this is the same every time. Okay, so memorize it if you have to. Okay, so looking at number 7. Describe the end behavior of this. This time we're going to do it in words and arrow notation. Okay, we look at the fact that this is odd. Because it's odd, we know it's going to have end behavior like an n, just like a cubic function. So it'll either be like this, or it'll be upside down like this. It'll be one of these, okay? A right side up n, this is the positive version. An upside down n, then this is the negative version. But because this is a positive 2, then it should be the right side up n, just like a capital N. So we'll look at this one for the end behavior. On the left it falls, on the right it rises. Okay, on the left it falls, on the right it rises, and so that's what we would put in words. Now using arrow notation. Okay, so here we'd have the same thing using arrow notation. As x approaches negative infinity, f of x approaches negative infinity. That means on the left it falls. As x approaches positive infinity, f of x approaches positive infinity. On the right, it rises. Okay, let's do it again. By the way, you should not be watching this with a pen or a pencil in your hand. Watch the video, and then go back and do it yourself. All right, so right now, if you have a pencil in your hand and you think you know how to do number 8, stop the video. Do it yourself. All right, do not just copy off of me. Okay, describe the end behavior. So again, the key thing here for as far as the end behavior is the degree. This is even. Okay, this is even degree. Because this is even, we know that this is going to be some type of a parabola. Okay, it's either going to be right side up parabola. Okay, now let me be clear. I should say we know that the end behavior is going to be like a parabola. This won't be a parabola. This will actually have a bunch of bumps in it. Okay, it will be more like this. But as far as the end behavior, it's the same as a parabola. That looks like a snow-capped mountain. Anyway, I'm crazy. It's not a parabola, but the end behavior will be like a parabola because it is even. I missed. Okay, now because it is a negative leading coefficient, then we know that we should be looking at, because it is a negative leading coefficient, we know we should be looking at the upside down version. Okay, that's the negative version. All right, this is the positive version. So we'll look at the negative inversion. In other words, on the left it falls and on the right it falls. All right, I'm just going to copy. Going to copy off myself, make my life easier. Okay, so on the left it falls and on the right it falls. Okay, using arrow notation, okay, on the left it falls, so negative infinity. But on the right it falls, so that will also be negative infinity. Okay? By the way, you do not need these plus signs in front of the positive infinity. The plus sign would be understood. I'm just putting them here for emphasis. Negative infinity, positive infinity. But you don't have to put the plus sign. Alright, moving on. Number 9. Given the graph of this polynomial function, is the degree even or odd? I can tell whether the degree is even or odd based on the end behavior. Okay? Does it have the end behavior of a parabola? Okay? Or does it have the end behavior of a cubic function? Well, you see it has the end behavior of a parabola. Okay? Yeah, like I can almost just draw a parabola on it like this. So because it has the end behavior of a parabola, that's how I know that the degree must be even. Alright? Now, is the leading coefficient positive or negative? Well, is the end behavior like a right side up parabola, or is it like an upside down parabola? Well, you can see because of what I've been drawing. The end behavior is like an upside down parabola. So this function has even degree because it has end behavior like a parabola, and the leading coefficient is negative. There must be a negative in front because it's like an upside down parabola. Okay, so is the degree even or odd? Even. Is the leading coefficient positive or negative? It is negative. Okay, and I can tell all that just by glancing at the graph. That's my goal for you guys. Okay? Let me just quiz you further, just verbally. Let's just do one verbally. What if I had a graph like this? Okay, don't write this down or anything. Just do it verbally. All right, say this is function g of x. Now, does this function g, is this degree even or odd? All right, I'm hoping you can see that this would be odd degree. Okay, see how the end behavior goes in opposite directions? A parabola doesn't do that. Okay, so for when it's even, they always point the same direction. If you got one up, one down, that's definitely going to be an odd degree. So third power, fifth power, seventh power, like that. Just like a cubic. Now, a cubic can either look like this, all right, one down, one up, or it can look like this. Okay. Now, can you tell that this one, does this graph look like A or B in terms of end behavior? All right, I'm hoping you can see that the end behavior is like B. Now, let's talk leading coefficient. Is this the positive version or the negative version of the leading coefficient? Well, the way I tried to get you to learn it was the positive version is like a capital N, right side up. The negative version is like an upside down N. So is this like a right side up N or an upside down N? This is like an upside down N. Okay, this has the same end behavior as an upside down N. So this is actually the negative version. All right, A would have been the positive version. So we knew it's odd degree, and we also know that it has a negative, all right, leading coefficient. Okay, so there'd be a big old minus sign in front. Okay, that's the type of thing I want you to be able to do. You should be able to glance at any graph and tell me whether it's even or odd degree, and you should be able to tell me if it's negative or positive leading coefficient. All right, let's move on. Find the sum, difference, or product of the two polynomials. Well, adding polynomial is easy. You just combine like terms. Now, to be like terms, the degree of each term has to be the same. So 2x to the third power. Well, there are no x to the third powers in the other polynomial. But look at these terms. Negative 4x squared, 2x squared. They're both x squared. They're both quadratic terms. So those are like terms. We'll put those together. And then we have the constants, 5 and negative 1. So we will combine like terms. So, okay, 2x to the third power, it doesn't have anything to combine with, so we'll just bring that down. 2x to the third power. Negative 4x squared plus 2x squared. Well, negative 4 plus 2 is negative 2. And then the x squared just stays the same. When you combine like terms, the only thing that changes is the coefficient. Okay? And then finally we have negative 5 minus 1, so that is positive 4. So boom, there it is. Okay, notice it is not x to the fourth power or something. When you add, when you're combining like terms, only the coefficient is going to change. Now, you have to be careful of one thing when you're subtracting. Let me zoom in a bit. Before you go combining like terms, you have to treat this like it is a negative 1. All right, this minus sign is like a negative 1 sitting here. And you have to take this negative 1 and distribute with it, like this. Okay? If I multiply all these by negative 1, watch what happens. So I have negative 3x squared. All right? Then negative 1 times x is negative x. Negative 1 times negative 4 is positive 4. So I get this. All right? Now I can bring down the other one. So just bring it down. X squared minus 4x plus 2. Now I can combine my like terms. Okay? The x squared goes with the negative 3x squared. Those are like terms. The negative 4x goes with the negative x. Those are like terms. And the, you know what, I feel like I should have pink or something. Let's try this. Okay, the 2 and the 4, those are like terms. So these are the terms I'm going to be putting together. X squared minus 3x squared. Well, this is like having 1x squared minus 3x squared. 1 minus 3 is negative 2. So that's going to give me negative 2x squared. Only the coefficient changes. Keep the x squared. Now I'm putting these blue ones together. Negative 4 and this is like negative 1. Together that makes negative 5. And so negative 5x. And then of course positive 2 and positive 4 is positive 6. So that would be the answer to number 11. Do not watch this with a pencil in your hand. Okay, fine, watch the video. Alright, but then go back and do it yourself. You will not learn by copying. You'll only mess it up on the quiz. Now, this is multiplication. We are going to do the distributive property now. So I'm going to take this and I'm going to distribute and multiply by everything inside. Okay? When I do negative 3x squared times 2x squared, well, negative 3 times 2 is negative 6. X squared times x squared is x to the fourth power. Okay? Now, negative 3x squared times negative 4x. Notice they don't have to be like terms to multiply. Alright? Negative 3 times negative 4 is positive 12. Alright? Negative 3 times negative 4 is positive 12. Now x squared times x, all right? And in my head I'm thinking this, x squared times x. X squared times x is x to the third power. Okay, remember, x squared means x times x. So x squared times x means x times x times x, which is x to the third power. Another way to look at it is, this is x squared, it has a 2, and x is like x to the 1 power. And basically you add those exponents and get 3. Either way you want to look at it. So when I do x squared times x, I'm going to get x to the third power. And finally, multiplying this times 1 will just give me the negative 3x squared back. Okay, so that is how you multiply. All right, well, that's how you multiply by a monomial. You know, you do that distributive property. Don't forget how you multiply a binomial times a binomial. We're going to do the distributive property, but we're going to do it twice. We're going to take x and distribute, and then we're going to take negative 3 and distribute that. All right, but let's start with the x. X times 2x would be 2x squared. X times negative 5 would be negative 5x. Okay, now I'm going to distribute the negative 3. Negative 3 times 2x is negative 6x. Negative 3 times negative 5 is positive 15. All right, now hopefully you can see that these are like terms. So we will have 2x squared minus 11x, putting these two together, plus 15. All right, that is how you would do number 13. Binomial times a binomial. Now guess what? If I do a binomial times a trinomial, it works exactly the same way. Do not watch this with a pencil in your hand. If you have a pencil or pen, put it down. Watch the video and then do it yourself later. Anyway, I am going to distribute the 3x, okay, to all three. And then after that, I'm going to turn around and distribute the 2. All right, and I'm going to color code it so you can see exactly what I'm doing. So if I distribute this 3x, 3x times x squared is going to be 3x to the third power. X times x squared is x to the third power. 3x times negative 5x, that's negative 15. Okay, 3 times negative 5. Then x times x is x squared. Finally, 3x times 4 is positive 12x. So there, I distributed the 3x. All right, now I'm going to switch to red, and I'm going to distribute the 2. So I'm going to do 2 times x squared. Now, I could just stick this on the end, but I know I'm shooting for like terms later. So 2 times x squared, I like to line these up. So 2 times x squared is 2x squared, but I'm going to go ahead and put it underneath the like term. 2 times negative 5x, well, that's negative 10x. And again, I would like to line that up with the like term. And then 2 times 4 is 8, and there is no like term, so I'll just put it here on the end. All right, if I do that, it just makes everything easier, because now all I have to do is bring everything straight down, combining like terms as I go. So the 3x to the third power just comes down. So 3x to the third power. Negative 15, positive 2. That's negative 13x squared. Stays what it is. Positive 12, negative 10. That's positive 2x. And then just bring down the 8. Okay, so that is how you multiply a binomial times a trinomial. Number 15 is practically the same thing. If you have not tried to do number 15 yet yourself, stop the video and do number 15 yourself. All right, if you're watching the video because you don't know how to do it, do not copy. Do not watch this with a pen or a pencil in your hand. Do it. Watch the video and then go do it yourself. Alright, so once again, you take your x squared and you distribute that first. Okay, if you do that, x squared times 2x squared, that's going to give you 2x to the 4th power. Then x squared times 4x, alright, that'll give me 4x to the 3rd power. X squared times x is x to the 3rd. Then if I do x squared times negative 7, that's going to give me negative 7x squared. So there I've distributed the x squared so far. Now I'm going to distribute the negative 3. Alright, you know what? I need to move this out of the way if I can. Okay, so I'm going to take the negative 3 and I'm going to distribute that. Okay, and if there are any, I am going to try to line up my like terms. So negative 3 times 2x squared, that's negative 6x squared. So that would be like right here. And then negative 3 times 4x, that'll be negative 12x. It doesn't have a like term, so I'll just stick it on here. And negative 3 times negative 7 is positive 21. Alright, well I only had one pair of like terms that time. So the whole stacking thing was not a big help this time. But I get x to the 4th power. Alright, just bringing these guys down. So x to the 4th power plus 4x to the 3rd power. Negative 7 and negative 6 make negative 13x squared. Alright, that stays the same. And then I just bring these down. So minus 12x plus 21. Okay, so this would be the answer number 15. Alright, number 16. Alright, well, if I want to multiply 3 binomials together, the key is to do just do 2 at a time. So so this is what I'm saying to you people. What you really want to do is start off by just doing these 2. Alright, forget about the other one. Just do x plus 3 times x plus 1. Okay, so if I do that, alright, so I'm going to distribute that x. Alright, and so x times x, that's x squared. Alright, x times 1 is x. Alright, then I distribute the 3. 3 times x is 3x. 3 times 1 is 3. Okay, if I put those together, I get x squared. Alright, x plus 3x. Alright, putting these together, that's 4x plus 3. So that's what I get from multiplying these 2 yellow ones together. Okay, so I get this trinomial. Now I'm just going to bring down the x minus 2. So now I have a binomial times a trinomial. Well, isn't that just what we did before? Look at number 14, binomial times trinomial. So now the rest of number 16 is just like 14 and 15. Okay, so in other words, hold on, let me see if I can give myself a little more space to do what I gotta do. Okay, so once again I will do the distributive property. So I'm going to take this x and I'm going to distribute that. Okay, so x times x squared is x to the 3rd power. X times 4x is 4x squared. And x times 3 is 3x. Then I'm going to take this negative 2 and I will distribute that. Negative 2 times 4x is negative 8x. Okay, I'm just checking to see if there's anything good going to happen. Okay, negative 2 times 4x is negative 8x. All right. Wait, okay, I knew I was messing up something. Negative 2 times x squared. I don't know why I'm skipping that for a second. Negative 2 times x squared is negative 2x squared. And I will go ahead and line that up then. And then negative 2 times 4x is negative 8x. And then negative 2 times 3 is negative 6. Okay, if I combine like terms, well, I'm just going to bring down my x to the third power. 4 minus 2 is positive 2x squared. 3 minus 8 is negative 5x. And then the minus 6. Okay? There's number 16. Alright, number 17 is the same thing as number 16. It's just starting out in a more compact form, right? But we could quickly take this and do 2x plus 1 times 2x plus 1 times 2x plus 1. All right, if you have something to the third power, it means multiply that thing times itself 3 times. Notice I cannot just cube the 2x and cube the 1. That does not work. All right, instead I have to do number 17 the same way I did number 16. If you are watching this video, do not have a pencil or a pen in your hand. Watch the video, but then go back and do the problem yourself later. Okay, so just like I showed you on the last problem, the best thing to do is first do these two. Okay, so that means take your 2x and distribute like that. All right, so 2x times 2x is 4x squared. 2x times 1 is 2x. Then I take the 1 and I distribute that. All right, 1 times 2x is 2x. 1 times 1 is 1. If I put these together, all right, I'm going to get 4x squared plus 4x, all right, putting these together, plus 1. Okay, I get this trinomial out of it. Now I'm just going to bring down the 2x plus 1 from the beginning. Alright, I just brought that straight down. Okay, but now it is time to do the distributive property again. So I will take my 2x squared and I will distribute. If I do that, 2x times 4x squared, that's going to be 8x to the third power. 2x times 4x is going to be 8x squared. And 2x times 1 is just going to be 2x. So I took the 2x and I distributed. Now I'm going to take the 1, the positive 1, and I'm going to distribute that. Alright, well 1 times 4x squared is going to be 4x squared. 1 times 4x is 4x. And 1 times 1 is 1. Alright, combining any like terms, I will have 8x to the third power. 8 plus 4 is 12, so I'll have 12x squared. Notice the x squared doesn't change when you combine like terms, just the coefficients. Same thing here, this x will stay x, but 2 plus 4 is 6, so I'll have plus 6x plus 1. So this would be your answer for number 17. Okay, last one, number 18. I think I'll need a little bit more space. Okay. Once again, we are going to do the distributive property. But this time, we have to distribute 3 things instead of 1. Instead of 2, I'm sorry. So I'm going to start with my x squared, and I'm going to distribute that. So I'm going to multiply everything by x squared. Okay, if I do that, x squared times x squared, that's going to be x to the 4th power. Okay, x squared times 4x, that's going to be 4x to the 3rd power. And then x squared times 2 is going to be 2x squared. So that's what I get so far. All right, now I'm going to distribute this negative x. So if I take negative x and I distribute that, let's see what I get. Okay, well, negative x times x squared is going to be negative x to the 3rd power. All right, it's like, sort of like having negative 1 x to the 3rd power. All right, because this is like having a negative 1. Okay, negative x times 4x is negative 4x squared. See how I line up the like terms? I highly recommend doing this. All right, and then negative 1x, or negative x, times 2, that's going to be negative 2x. Okay? Now, but I still have to distribute this negative 3. Okay? I guess I think I'll use gray. I'll use gray. Alright, so if I distribute the negative 3, so I'm doing this. I'm doing negative 3 times x squared and negative 3 times 4x and negative 3 times 2. Alright, if I do negative 3 times x squared, that's negative 3x squared. So that would line up right here, negative 3x squared. If I do negative 3 times positive 4x, that's going to be negative 12x. And that would go right here. And then if I do negative 3 times positive 2, that would simply be negative 6. Okay, so it's the same thing as we did before, but we had to distribute 3 different things instead of just 2 or 1. But, you know, same concept. And then, like we always do, in the end, we have to combine any like terms we have. X to the 4th power is just going to come down, so that'll be x to the 4th power. Like terms, so positive 4 and negative 1, so that'll be positive 3 x to the 3rd power. Okay, x to the 3rd power doesn't change. Now, let's see. Positive 2 and negative 4. So far, that makes negative 2. So if I take that negative 2 and a negative 3, that'll make negative 5. So we have negative 5x squared. X squared, x squared, x squared, x squared. Notice the x squared does not change, only the coefficient. Negative 2 and negative 12 make negative 14. So it's negative 14x. And then you bring down your negative 6. Now that is a very crooked line. Maybe I'll even cheat and make a box. Okay, so there would be your answer to number 18. And I think that's the end of this whole lesson. All right, I hope this was helpful. Please make sure that you can do every problem on this paper by yourself without copying. If you found yourself copying this, you should print out a blank copy of this and do it over again. Or, you know, just bring up a blank copy on your screen and then do it on scratch paper. Okay? Because if you can't do it yourself, you won't be able to do it on the next quiz or test, and, you know, you won't get the grade that you are hoping for. I will see you on the next video, people.